In previous lectures, we installed Truffle and Ganache that can easily emulate an Ethereum node for development purposes. While these fake Ethereum nodes are an easy way to test your application, you have to keep in mind that they are just emulators. They provide the same interface as an Ethereum node deployed in the public Ethereum network, but internally they work completely differently. If you want to ensure that your contract will run properly on the main network, it is highly recommended to test it with a full Ethereum node. In this lecture, we'll install a private Ethereum instance with Geth on Linux. If you are on macOS or Windows, please use one of the other dedicated lectures for those systems. Now let's start by creating the folder that will host the database and the accounts for our private node. To do that, let's open a new terminal and run mkdir -p chainskills/private. So we're doing this from our user home directory in order to create our private data directory inside the chainskills directory inside our user home directory. And then we can go to chainskills/private. Now, before creating our private instance, we have to define the genesis block, that is the block that will define the initial behavior of our blockchain instance. Creating a genesis block file from scratch can be painful, and reusing an existing one can be a problem if its version is older than your current installation of Geth. To ensure that your genesis block file is compliant with your version of Geth, we'll create it using a tool called Puppet. Puppet is a command line tool installed in parallel with Geth and provides features to create and monitor your own Ethereum network. Here we will use Puppet to create the genesis block file. So first, make sure that you are within the private directory, that the current directory is the private one, and then you can start the Puppet command. The first thing we are asked is the name for our network that we want to administer, and we'll call it Chainskills. Then we have a menu with a series of commands, and we'll choose the second one to configure a new genesis. Then it asks for the consensus engine that we want to use. We have a choice between Ethash and Click. Click being a proof of authority consensus algorithm, and we want to use one that's closest to the mainnet, so we're using Ethash. Number 1. Which accounts should be pre-funded? None, so we can just type enter here. And then we have to specify the network identifier. For this network identifier, we must choose something different from those that are used and reserved for public networks. Number 1 is for the mainnet. Number 2 is for the modern testnet, that's now obsolete. Number 3 is for the Robston testnet, that uses a proof of work consensus algorithm, so it's also a test network. Number 4 is for the Rinkaby test network, and this one uses a proof of authority consensus algorithm. And number 42 is reserved for the Parity public test network. So in our course, we would use the network ID 4224. So you can type 4224. Anything fun to embed into the genesis block, you can ignore that and just type enter. So now we created our genesis, but it's still in memory and we need to export it into a file. And to do that, we choose the second command, manage existing genesis. The second command again to export the genesis configuration. Then we ask for the file name, and by default it will be chainskills.json, so we keep the default, we just type enter. And we can see that it successfully exported the existing genesis block. And that's all we need to do with Puppet. So we can quit by typing Ctrl+C on our keyboard. And if I now list the content of the private directory, I have my chainskills.json file. Now let's open it in Atom. So here are the most interesting items that this Genesis file contains. The config section is a section that is used to define parameters for the chain. The network ID used for this instance is specified in chain ID. And config also contains the block numbers from which to apply various hard fork rules that have been added to the Ethereum chain over time. For example, the Byzantium hard fork will be applied from block number 4 on our private network. Then we have timestamp. So timestamp is used by Ethereum to adjust the level of difficulty that must be applied by the consensus algorithm. If the timestamp difference between two consecutive blocks is too small, the difficulty will be increased. If the timestamp difference between two consecutive blocks is too high, then the difficulty will be reduced. By the way, the timestamp is also used to ensure that blocks are in the correct order. Then we have extra data, where we could have set up some custom data here, but we didn't. Gas limit defines the maximum value of total gas that transactions in a block can spend. And this value is here to limit the processing requirements of each block, and in effect limit the size of blocks. In a private node, you can set this value to the maximum while keeping in mind that you have to measure the gas spent by your transactions. Then we have difficulty, that defines the difficulty level that will be used to validate a block, which directly correlates to the average number of times that a miner will have to run the hashing function to solve a consensus puzzle. On a private blockchain instance, it is recommended to set a lower value to reduce computation time. Then we have the Coinbase address. That is the one that will get the mining rewards for this block. For now it's 0, but then it will be replaced with the address of the mining account. Then we have the alloc section that is used to pre-fund certain accounts. It's very long, so we just reduce it. Number is the block number, so it's the genesis block, so the block number is 0. Gas used is the sum of all the gas used by all the transactions in this block, and there are none, so the gas used is 0. And finally, parent hash is the hash of the previous block. Here we are in the genesis block, the first one, so it's the only one that doesn't have any parent, and the parent hash is 0. Now that we have our genesis file, let's use it to initialize our private node. The private node will be created using the geth command with the following parameters. Datadir will be used to set the target directory where the private node data is saved, knowing that without this parameter, the node would use the folder for the main public node, and that's not what we want. And also we'll use this command to initialize the node with the genesis block that is in this file. So we can now close Atom. Make sure that we are in the private directory. Clean up terminal a little bit. And then we can type geth --datadir dot, that means the current directory. And then init chainscales.json. Okay, so we'll store the files for this chain inside the private directory, and we'll use the chainscales.json that is in the same directory. And here we can see that everything worked successfully. So the database will be under chainscale/private/geth/chain-data, and everything looks fine. And at this stage, this command created two directories, one for the geth chain data, and another one that is called keystore that will contain our accounts. And if we go to list the content of the keystore directory, for now it doesn't contain anything. Now we will create 3 accounts that we'll use during this course. The first one will receive the mining rewards, and the other 2 accounts will act as the buyer and or the seller of articles in the chain list decentralized application that we will build later. To create those accounts, we will use the geth command and specify the path of our private node data directory and the account new command. So here, geth --datadir again, dot, and then account new to create a new account. Here we have to specify the password for the account. So in our case, we will use pass1234 for all accounts on our private node. We have to confirm it, 1234. And here it created randomly this first account, FDBC, whatever, and this will be our first account. And we can run this command again, a second time, to create a second account with the same password, to make it easier later, and a third time to create a third account. So our 3 accounts are created and they each have a unique address. Of course, these addresses will be different for you because they are randomly generated. And the private keys of these accounts are located under the key store folder. So now if we list the content of the key store directory again, we have 3 files in there and each file corresponds to 1 account. So it contains 1 private key. Now to list these accounts and get their respective position, we can also use get --datadir account list. And here we get a list of accounts. Oops, sorry. Yeah. --datadir dot account list. And here we get a list of accounts, account 0, 1, and 2. With the file path where the key is stored, the address of the account, and everything. Note that by default, the first account, the one with index 0, is the one that will receive all the mining rewards when we start mining. So far, we initialized our private node and we created 3 accounts for it, but it hasn't started yet. In order to start our private node and mine blocks, we will create a script that will define all the required parameters to let us interact with our private node. Note that this startnode.sh script that we will create in a moment is attached as a resource to this lecture, so you can download it as is and run it as it is. We'll just go over the content of this file to explain each parameter. So here we'll use Atom to create this startnode.sh file inside the private directory. And then we can type the command. So of course it's get. It has a first argument that's called network ID. And here we'll use 4224. We want our node to mine right away. So we'll use the --mine option. And we can also specify how many threads it will use on our machine. So here I will specify miner threads 2, for example, to use 2 threads. You decide the number. The default is 3, I think. Then we need to specify the datadir again. And since we will run this from the private directory every time, we can just specify dot, because it is saved inside the private directory. Then we want this node to be isolated, not to connect with any peer. So we will deactivate the discovery protocol. So --no discover. But we want to enable the RPC endpoint because we'll use it to connect to it from the MetaMask extension later. --RPC. We also specify the RPC port, which will leave with the default, so RPC port, and that will be 8545 within double quotes. And even though the discovery protocol is deactivated, we can also specify the discovery port that is by default 30303. Next thing, we want to be able to connect to the RPC endpoint from any domain. So we need to add an option for that, RPC course domain, and that would be a star. Then there's this obscure NAT option that we'll configure with any. And then we need to enable a certain number of modules over the RPC endpoint. And to do that, we need to add RPC API as an option. And then we can list the modules separated by a comma. So ETH, comma, Web3, comma, personal, comma, net. So those are the 4 modules that will be enabled over the RPC endpoint. Then, since our node will mine, it will need to unlock an account for adding blocks to the chain. And so we can add the unlock argument and specify the index of the account to unlock. And it will also need a password, so --password, that will point to a file that contains the password. And we'll create that file in a second. Actually, I think we should remove the double quotes. And the last parameter is probably one of the most important. It's the --IPC path. So when our private node will start, it opens an IPC endpoint. So in addition to the RPC endpoint, it also opens an IPC endpoint. That will be very useful for other Geth tools like Mist or the Geth console that will open soon. And basically what this does is specify the path on which to create this IPC endpoint so that other tools can find it automatically. So here we need to specify a value that corresponds to the default path where other tools will look for it. In our case, that would be in the user home directory under .ethereum/geth.ipc. So by default, all the other Geth tools will look for this IPC endpoint under the .ethereum directory of the user home directory in the geth.ipc file. This is very important. If you mess up that one, you will have problems later on when you want to attach a console to your running node. One other important point is to make sure that all this command fits on one line, because if you put it on several lines, if you add some line feeds or card returns to this file, everything that's not on the first line will be ignored, and then you will have issue with configuration. So again, make sure that it all fits on one line, and then save the file. Now, before we can run the script, we also need to create this password.sec file that we reference here. To do that, we can right-click on the private directory, create a new file, and call it password.sec. And here we can just add pass1234, which is the password for account 0 that we are unlocking. Then before we can run the startnode.sh script, we need to make it executable. So in the terminal, within the private directory, we can use chmod +x, startnode.sh, and now it should be ready to run, startnode.sh. So I will stop it right away just to show you the important information that we get at the beginning. So when our node starts, we get some very interesting elements. First of all, we can see that the instance is using Geth 173, which is the version that we installed, so that's good. We can also confirm that the database is created inside the private /geth/chain data directory, so that's okay. We can also find the configuration that we inserted in the Genesis block, so the chain ID is 4224, and then we have, for example, the Byzantium block that will start on block 4. We also have the Ethash caches, and we'll talk about that, Ethash DAGs that are saved under the ethash.ethash directory in the user home directory. We'll talk about that later. Just keep in mind that we can see that here. And what else? So we can see that the HTTP endpoint was opened on port 8545, so that's good. And the IPC endpoint was opened on the user home directory under .ethereum/geth.ipc, which is the right location. So always check that value very carefully. If this is not correct, for example, if the geth.ipc endpoint is opened inside the private directory, you will have a problem later. So make sure that this is correct before going further. And we can also confirm that the first account, so that's the Coinbase account, was successfully unlocked. And right away, it started the mining operation and it committed new mining work. And then we interrupted everything. So let's start it again. And let it go this time. And there, what you can see is a list of lines that say generating DAG in progress. And in each line, you have a percentage element that shows you the progress of this process. Now the DAG, or directed acyclic graph, is a data structure that is needed by the Ethash mining algorithm to do its work. It is generated every 30,000 blocks, and a period of 30,000 blocks is called an epoch, which you can see here, epoch 0. And it is stored in a file under .ethash in your user home directory. Generating it will take some time the first time, and it may even take a few hours on some machines. And again, you can follow the progress of this task by looking at the percentage part of these lines. When this percentage reaches 100, it will display a line saying generated Ethash verification cache, and the DAG generation process will start again for epoch 1. When the second iteration reaches 100%, mining will be in full power. Now, since Geth maintains the next DAG in parallel with mining, you shouldn't have to wait for new DAGs to be generated after block 30,000. This process takes some time, but only the first time, and then that's it. So here we can see we're already at 62% for epoch 0, and we need to wait for it to finish epoch 0, and then it will start mining. So while it's generating the DAG, just a word of warning, if Geth seems to be stuck for several hours on one of these steps, it might mean that you forgot to initialize your node with the Genesis file, or you forgot to create some accounts, or there is a mistake in your startnode.sh, or your chain data is corrupted for some reason. So your best option is just to delete the private directory altogether and to do the whole procedure again. Don't forget that you can download the startnode.sh script and the Genesis file from the resources attached to this lecture to be sure there is no mistake in it. And if after all that your private node doesn't start mining as it should, feel free to copy-paste as much of your startnode.sh console output into a question in the Q&A section of this course, along with the content of your startnode.sh script, and we will help you troubleshoot what's going on. So here we can see that epoch 0 was completed, and right away it started mining potential blocks. So every time you see a line like this with a kind of a pickaxe icon, it means that it started mining a block. So now it's mining blocks and generating DAG in parallel. And when the DAG will be generated for epoch 1, it will just keep mining. So my advice is to wait for generating DAG for epoch 1 to be complete before running any command, because then those commands will be faster. So here we reach the end of the DAG generation process for epoch 1, and you can see that it's just mining new blocks. One important note at this point, you might be worried about the fact that your node is mining new blocks, even though there are no transactions sent to this node. And you have to remember that the mining process is not just there to mine new transactions. It's also there to secure your data and also to create new cryptocurrency, new Ether. So on a normal proof of work implementation, new blocks are generated on regular intervals of time, whether there are pending transactions or not. So you can perfectly have blocks that are completely empty of transactions, but are just here to generate a new quantity of Ether. And you can even find such empty blocks on the mainnet. So keep that in mind. Our private node will keep generating new blocks, even if there are no transactions in them. So now that our node is mining, we can open a new terminal. Okay. And we keep the private node running in the background, but we'll run geth attach to attach a geth console to our running node. So here we can connect to our node, and we can confirm that it's connected to the right one. Well, actually, we only have one running, and you should always make sure that when you run your private node, you don't have a mist or another geth instance running on the mainnet, for example, because they all use the same RPC ports by default and the same discovery port. So that's 8545 and 30303 by default. Here we can see that the data dir is correct. So we are connecting to a node that's storing data in the private directory. And we can also confirm that the Coinbase is the same. Now, if you get an error like unable to attach to remote geth, dial Unix, geth IPC, no such file or directory, that means that your geth.ipc endpoint is not opened in the right place. So again, make sure that you check the beginning of the console output for your start node script running and check the content of your start node script. Now let's review some of the commands that we can use within this JavaScript console. eth.accounts will list the accounts registered on that node. And eth.coinbase will give us the first account, the one that is receiving mining rewards. By the way, the coinbase.com marketplace is named after this concept. We can also query the balance of an account by using the eth.getBalance function and pass it the address of the account that we want the balance for. And it returns a number of Wei being the smaller unit of value of cryptocurrency, and it actually corresponds to 10 to the minus 18 Ether. And to avoid any unnecessary calculation, we can use the web3.fromWei function to actually convert that amount into Ether. So we just indicate the address of the account that we want. We have actually from Wei, eth.getBalance. Here we specify the address of the account for which we want the balance. And the second parameter to from Wei is the name of the unit that we want to convert into. So here we can see that our node, that our Coinbase account already has 147 Ether in it. And of course, we can do the same for accounts one. So here, just precision, I'm running inside a virtual machine, so I don't have my native keyboard. I'm going to use a trick with Linux, but if you have a real keyboard, you shouldn't have any problem with that. So here, I'm going to access accounts one. And where's the closing here? Okay. And I want that in Ether. Oops, I forgot to close my command. Okay, I forgot one parenthesis. And here we can see that account one has 0 and account two has 0 as well. Another command that we can use is miner.stop to stop the mining process. So if I do that, and I go back to the other window, I can see that the mining process has stopped. And then I can restart the mining process with miner.start. And in parameter, I can even specify the number of threads that I want my mining algorithm to use. So here I'll mine on 2 threads. I can also use net.version to get the chain ID, the network identifier. And last but not least, I can also use the personal.unlock account to unlock an account. So an account is associated with a private key, and this private key is protected with a password. So if you want to be able to use an account to sign a transaction, you first need to unlock it. So here, for example, we want to again use unlock account 1. Okay. And we then need to specify the password, pass1234 in double quotes. And then we can indicate the duration for which we want to unlock the account. So for example, 300 seconds, that will be 5 minutes. And when we get true, it means that the unlock account was successful. We can also do it just by typing the address of the account eth.accounts2 without any other parameter, and then we can type the password directly on the prompt, and it will be unlocked for the default duration, which I think is 10 minutes. By the way, you can find a comprehensive list of commands right on this link that we'll also add to the resources of this lecture. Now, before closing this lecture, we will transfer some ethers from the Coinbase account, the one linked to the mining process, to the other two accounts. Okay, so again, we can check the balance of the Coinbase account, and it's now 267 ether, and we'll transfer 10 of these to account 1 and 10 to account index 2. To do that, we'll use the send transaction command on the ETH module, so send transaction, and that function takes only one parameter in the form of a JavaScript object. And this JavaScript object will have three fields. The first one is from, and that is eth.coinbase in our case. The second one is to, that will be eth.accounts1 first. And the third one is value, and for that we need to indicate a number of way. So before we use from way to convert a number of way into a number of ether, now we can use to way in the other way around, to way to convert 10 ether into way. And when we run that command, we get this long string. And this is actually the transaction hash for the transaction that was created. And if we go back to the running node in the background, we can see that this transaction was submitted, and then it will be mined in a subsequent block. So now we can go back to the console, run this command again to do the same transfer, but to account with index 2. A new transaction was created and submitted to our running node. That's this one. Okay. And then we have to wait for a few seconds for those transactions to be both mined into blocks. And then we can go back to the console and check the balances again. So let's check the balance of accounts 1 first. And there we have our 10 ethers, and we can do the same for accounts 2. And there we have our 10 ethers. Again, this works because our node is mining, so as soon as we submitted transactions to it, it started mining them into new blocks. At any point, if you need to quit the Geth console, you can just type exit. Oops, sorry. You can just type exit, and it will exit this console. And then we'll close this terminal here. And to quit the running node, you can just type Control-C in it, and it will interrupt the process. So in this lecture, we explained how to create a Genesis block using Puppet. We initialized a private node with this Genesis block. We created a couple of accounts. We started the private node. We attached a console to it, and we checked the list of accounts and their balances. After which we sent some ether between accounts. And we also started and stopped the mining process from the console. Again, note that you can find the Genesis file and the startnode.sh script attached as resources to this lesson. In the next lecture, we'll show you how to set up MetaMask in Chrome.